And then as well, we also have the net specificity, which is based on the same principles. We have one for the sequential testing and then one for simultaneous testing. When we're looking at sequential testing for specificity, we're looking to see if someone without the disease has a negative value. And if you look at their circles, they're not colored in because nobody has the disease. And then it still has that overlap. So sometimes people will test negative for the disease. Sometimes they'll test negative for the disease in test 1 or test 2 or both sometimes. So the specificity, the net specificity in a sequential test, so when we bring a group of people together, we give them our first test, we need these people to test negative in that first test, or in that second test. They won't be necessarily included in that second test if they test negative. So they have to test negative in either case. So you want, again, it's that OR function, and because they're independent and there is that overlap, we have the probability of someone testing negative on test 1 or test 2 is the net specificity is the specificity of test 1, the chance that we say that there's not a disease when there is not a disease, plus the specificity of test 2 minus that overlap, which is the specificity of 1 times the specificity of 2, the probability of saying we don't have a disease when we actually don't in both of those tests. In the simultaneous case, when we give a test at the same time, we're looking for someone that will test negative for both cases. We want, if they're going to come up negative and I am giving them multiple tests at the same time, they have to come up negative in every single one of those tests, otherwise they would be considered positive. So in the simultaneous case, for net specificity, we're going to use the AND function, and it's going to be the probability of testing negative for both tests is equal to the chance of testing negative for the first test, which is the specificity of 1, times the chance of testing negative for the second test when you don't have the disease, which is the specificity for test 2. So overall, in simultaneous testing, when you have multiple tests done at once, you get a higher sensitivity, so you're able to detect those people that have the disease when they actually have the disease. But you get a loss of specificity. So when you're compared to the individual tests, you get a loss of specificity. So in this case, our specificity is very close to our probability. We don't have to subtract anything based on the overlap for the specificity. So in simultaneous testing, you get a net loss in specificity and a net gain in sensitivity. In sequential testing, on the other hand, when we're looking for somebody that's positive in either of the tests, there's a net loss in sensitivity, but a gain in specificity when you're comparing it to those original tests. And I'll have an example at the end of the lecture to go through that a little bit more. And here is the example. So when we're looking at 2 tests, this is a sequential test. This is first you're getting tested for blood sugar to see if you're potentially at a level that could be considered diabetic. And then after you are positive for this test, you will go to a second test. So in the first test, the prevalence of diabetes is 5%. So we have 10,000 people, and the prevalence is 5 times 10,000 or 500. So 500 people have diabetes, which means 10,000 minus 500 or 9,500 people are without diabetes. And then here's our test. The sensitivity is 70 and the specificity is 80. So the specificity is the number of people with the disease, 500, times the sensitivity will give us that true positives. Our sensitivity is the number, the proportion of the people with the disease that actually test positive for the disease. And the specificity is the proportion of people that don't have the disease that test negative. So that's going to be 80 times 9,500 or 7,600. And then the rest of it is just algebra to figure out the false negatives and false positives. You should be able to do all of those cases. So if I give you a sensitivity or a specificity, you should be able to figure out the true positives and true negatives. And of course, if I give you the prevalence and the population as well. So then we do a second test, and you see that we take everybody that tested positive in that first test, and they become our new population in the second test. So only people that tested positive for that first test will be included in that second test. So when we're filling in all these blanks again, we just look at the sensitivity and the specificity of that more expensive, more invasive glucose tolerance test. It's a little more hard to do, and we have a higher sensitivity and a higher specificity. We would give that test to everyone, but it's too expensive and time consuming. So now we only want to give it to those people that we think have the disease based on that original blood sugar test. Then, so then we take our sensitivity and specificity based on the number of people with the disease to find our test results. So if you multiply 350 by 0.9, you get 315. If you multiply 1900 by 0.9, you get 1710. Just a reminder, again, you should be able to manipulate those tables. And then we get the net sensitivity based on this sequential testing, which is the probability of having someone be positive at both of these tests, which is only people that are positive to this test are going to be included here. So this 350 indicates that people have already tested positive. So the people testing positive to both of these tests are only the people down here, 315. And then that is a sensitivity measure, so it's to all of the people with the disease. So we left 150 people in this first test that have the disease. So we need to include them too in our measure of sensitivity, net sensitivity, which is going to be 315 over everybody with the diabetes, which is 500. So it's 63%. And as you can see, sequential testing reduced the sensitivity in both cases if you're comparing them to each of those. And then we look at the new or net specificity by looking at the number of people that tested negative to either of the tests. With sequential testing, you're going to get knocked out if you test negative in either of the tests. So in this case, we have 7,600 people tested negative in that first test, so they're part of the numerator. And then the 1,710 tested negative in the second test, so they are also in the numerator in that second test. And that's over all of the people that don't have diabetes, which is in that first test. That 1,900 is encompassed into that 9,500, so we don't have to add that twice. We just want people that have the disease and don't. So that's our new or net specificity, and as you can see, when we're doing sequential testing, our specificity goes up. So we're better at looking in comparison to those original two tests on their own, we're better at detecting the people that don't have disease, but we're worse at detecting the people that do have the disease. A little bit more on the positive predictive value. Okay, so the positive predictive value, again, it answers the question of what proportion of patients who test positive actually have the disease. So if I run this test 1,000 times and 800 people come up with a positive value, I can expect a certain amount of them to actually have the disease. It's important in that respect to public health. It's a measure of, based on the test, based on the disease, based on the prevalence of the disease, how much we can actually expect of the disease. Okay, so then it also has a, as I said, a direct relationship to disease prevalence. And as the prevalence goes up, we talked a little bit about this before, as the prevalence goes up, the positive predictive value is going to go up as well. You can think about that kind of like when in statistics, when you have a higher population, you have less variability, and you're going to have a better measure. So that is what is meant by a direct relationship with disease prevalence. The negative predictive value has that same relationship with prevalence, but in the opposite way. So as in a lower prevalence, we're going to be better at predicting that people don't have the disease, and we'll have a higher negative predictive value. When you have a high prevalence within a group, it's considered a high-risk group. So our positive predictive value, a test that has a high positive predictive value is going to be good in a high-risk group, such as, so like later in life, we're going to have higher prevalence of heart disease, say. So we're going to want to use a test that has a positive predictive value for that high-risk group. So that's why after a certain age, you start getting tested for prostate and breast cancers, because that's a high-risk group. The positive predictive value of a test does not translate from a high-risk group to a low-risk group. So for example, if there is a indicator of the potential for having a heart attack, and that positive predictive value is based on a high-risk group of, say, older individuals with a poor diet, they will, if they try and use that same test on a healthy group, say, with a low risk of heart attack, say young people for admittance into the fire academy, then they're going to have a lot of false negatives. They're going to reject a lot of guys and gals that will not have a potential for heart disease. So the positive predictive value of a test based on prevalence is not translatable to a different population. It's only on the population that it actually was measured in. The predictive value is based on prevalence, and it changes with the prevalence and the test values again. So if you look at these two examples, we have the prevalence of 10%, and that won't change, and then we have the sensitivity of 100%, and the specificity goes from 70 to 95%. If the population is 10,000 and you know the prevalence is 10%, then we have 1,000 people that have the disease, so that'll go in this box. And then it's just 1,000 minus 100, 10,000 minus 1,000, or 900. So 900 will be without the disease in this box. And then just to review, we know if the sensitivity is 100, everybody that has the disease has a positive test, so all 1,000 cases will go up here, and all 1,000 cases will go up here, and there'll be 0 in the cases of false negatives. And then because we know the sensitivity, the specificity here at 70, we have 9,000 times 0.7, so that'll give us 6,300, and those are the people here, the true negatives. And then it's just a matter of subtracting values to get the rest of your totals. I'm going to pause there for a second and switch it over.